Hello, in this lecture we're going to look at line segment to line segment intersection. So this is something that's important for completing the homeworks and in particular creating our discretized spaces. So when you're thinking about two line segments intersecting, in this case two line segments in 2D vector space, we could either solve for the point of intersection if there is one, or we could just say yes or no, there is an intersection. So in this lecture, we're just going to look at the predicate form that returns true or false, depending on true if there's an intersection and false if not. So we're going to start by looking at the area of a triangle. So that you might think, what does the area of a triangle have to do with line intersection? And so we'll have to build up to that, and then it will become apparent once we define a few things here. But you're probably familiar with the equation for area of a triangle: half base times height. And then you may have also seen the vector form computing the same thing, but if you have vectors defining your triangle, you can perform the cross product on, say, you have a triangle as shown in this figure on the slide. So we have segments A and B. So there's vector A, which goes from point A to point B, and then vector B that goes from point A to point C. So if we take the cross product of A cross with B, then the magnitude of that resulting vector would be the parallelogram that is like double our triangle. So from that, we can divide by 2. So that would be a way we can define it. And in terms of the different terms of the vector relative to the dimensions, so the cross product has to be 3D. So that's why the result here has the unit vector I, unit vector j, and unit vector k. So that is like the x, y, and z dimension. So most of the discussion of creating discretized spaces involves 2D, but we'll see in a minute that that's fine. A little bit about the cross product. If we don't take the magnitude of the cross product, there's more information we can get out of this. So depending on whether you have a right-handed coordinate system or a left-handed coordinate system, that will define which direction the cross product in the positive direction will go. So we'll use a right-hand coordinate system. So A and B cross together in that order, A cross B, will result in our cross product vector going in the up direction. And otherwise, if you like flip the order, it'll go in the negative direction. So now we want to work with 2D triangles. Again, just the nature of how we're representing our discretized space. So that's easy to do. So cross product is defined for 3 dimensions and 7, but we have no use for 7 dimensions. So we're going to use a 3-dimensional cross product. All we have to do is plug in 0 for the z value, so we can have the x and y components of our 2D position vectors, and then just add a 0 for z. So everything is in the xy plane, and Then when we perform a cross product with these two vectors that both have zeros for their z value, what you're going to have happen is that your x and y dimension terms, or the unit vector I, unit vector j, they will get zeroed out, and you'll only be left with your cross product either going up or down from the surface. And so everything is in that z value. So you might notice that to get the magnitude, there's no reason to do the square root of the sum of squares. You can just take directly the z value, the absolute value of that would tell you the magnitude. But we can leave the sign alone, like don't apply the absolute value. And that sign, the negative or positive associated with that z value that we get, will prove useful. So now we can define the area of the triangle based on the cross product, but the cross product knowing that our z is 0 and therefore several terms cancel out. And so that we get the equation that we see here on the top line of the slide. We can substitute in the form for these relative vectors. So each edge is defined by going from A to B. So that would be position vector B minus A. That defines edge A, or line segment A. Similarly for B, we would have C minus A to go from A to C. So we can plug that in, and now we have a new equation for the area that's based on the points of the triangle. So we have the 3 points of the triangle, and we have various terms. And I've moved the divide by 2, I moved it over to the area side. So we can call this the area 2. And one nice thing about that is, in terms of computational geometry, we can leave that as an integer, so we don't have to have a floating point representation. So anything that relies on area, we might generate and save in the form of twice area of the triangle until the last possible moment that we would finally need to really apply the division. Or, as we'll see, maybe we're only concerned about the sign. The area itself isn't really important. Now there's some improvement we can make here by reorganizing our equation. And by doing so, we can minimize the number of multiplies relative to the adds that are being performed. And this is beneficial because multiplication on a processor is typically, it takes more clock cycles than adds. So that's worthwhile. But the other thing is when we have 32-bit integers and multiplying that could potentially be pretty big, that's multiplies are more likely to generate an overflow. And so this new form shown on the bottom line, we're performing a subtraction first, which is in many cases likely to result in a smaller value before the multiply is applied, and therefore going to reduce the chance of an overflow. And basically it gives us a bigger working range of integers. So I keep mentioning the sign of the area. So if we have the vertices of our triangle ordered in counterclockwise order, then we can take the area of the triangle according to the form that we've been showing, like the A cross product with B. Again, assuming that our vertices A, B, and C are in counterclockwise order, and we're talking about a right-hand coordinate system, then that means we will that this cross product will always be positive for this particular triangle. But if we had vertices in a different order, then we would get a negative. And so this we can think of as being on the left or right side. So like from the perspective of A, if B is off to the left, like so if you extend the edge as an infinitely long line, so A becomes an infinitely long line passing through points A and B, then C is on the left side. But if C was on the right side, that would the result of A cross would be negative. So this is an interesting bit of information that we can leverage. In fact, we can use it to create these well-defined predicates for analyzing geometry. So if we use the equation for twice area of the triangle with 3 points, as following along with the form of the counterclockwise ordering with a right-hand coordinate system, so we could plug in like ABC with this left value, and it would be true, which that would we could use left to confirm that the triangle was in fact in the correct winding for right-hand coordinate system, the counterclockwise. We can also have a variant called left on. So rather than testing the greater than 0, we could test greater than or equal to 0. And this would include the possibility that there's no area to the triangle, which would mean it's like degenerate or perfectly flat. And furthermore, we could test for just equality with 0, and that would be a collinearity test. So A, B, and C are all in a perfect line together. So those 3 predicates give us a robust way to do lots of different computational geometry building up from these tests and contributing to other tests or algorithms that we might be interested in, including the intersection of 2 line segments. So we can see how this will be useful by considering a scenario where you have 2 line segments and you want to know how they intersect. So we have these line segments AB and CD. So an intersection will occur if and only if AB splits CD and CD splits AB. So you got to have both of those conditions met, which hopefully you can see from the figure, 2 figures shown here. But you can use left to make this determination for this, what the splitting is. So you can create a triangle like CD and B. So that would make you would be doing the cross product of the vector formed by C to D and the vector C to B. So the CD vector cross with CB, and that would be on the left side. But if you do the same thing with A, you would find A is on, so CD and CA, you'd find that CA goes to the right side because you get a negative value. So we could say that in that case that CD splits BA, but you also have to test the other way around. And what you're looking for is that they're different. So whichever line you're considering as the splitter, you want one call to left to be true and the other to be false, or vice versa. So that is 4 total calls to left, and you make a comparison just that they're not equal, or the XOR of each. And that's all you need. That'll tell you if there is any kind of intersection, which may be sufficient in a lot of cases for what you need. You may find for certain sorts of tests, you really got to make a distinction between the type of intersection. And this can be useful for more advanced sorts of tests. So the scenario we were looking at was really a proper test, but we can separate these out by considering things such as collinearity. So if we find, say, of course, uh, 2 points of an edge, those are collinear. But what if a point from the other line segment is collinear? So in that case, if we have at least one that is collinear, then we've introduced the possibility for an improper intersection. And then you could even have a situation where the line segments are coincident. So you can separate or distinguish between these different possibilities depending on how you set up the predicate logic. And so that this is useful. You can make a proper intersection test and an improper test. I'm not going to go into all those details, but the code used in the game AI assignments, like the base code or the computational geometry, does have this as an implementation. And you can also, if you're interested in more, you can check out the Computational Geometry in C book, second edition, with Joseph O'Rourke is the author. So that is really a pretty straightforward way of working with intersections. We don't actually have to solve the point of intersection, and it works. We can stay with the integer representation of the point, the endpoints of our line segments, and that makes for more robust sort of code for sort of operations that we would likely be performing when creating a discretized space. Hello. In this lecture, we're going to look at how to calculate the distance between a point and a line segment. So this is something that will be useful, especially with path networks, determining if there is anything too close to an edge between nodes. We want to make sure that there's enough room for our agent to safely traverse from one node to the next. And so we need some way to check to see if anything is within the radius distance of the agent to one of these edges. So if anything intrudes on that corridor, then that is not a good edge to use because the agent would not be able to follow it. So this calculation in terms of robustness, we will need to use a floating point representation. And this is because we're calculating an estimate of distance and just the nature of discretization to integers for computational geometry purposes. It's like pixels, and so the distances won't necessarily be aligned with the x or the y axis, and because they can be at arbitrary angles, that means we could have fractions of pixels, and so the estimates are probably being sub-pixel resolution, probably much more useful. So we'll work with floats. It will be we can manage things and keep the appropriate robustness that we need for our calculations, or at least in this situation. So you could either take if you've already mapped values to integers, you could use floats as provided that they're not that your values aren't already too big, which might, like your exponent too big, you might get to the point where each value might you might hit the resolution of the floats, like the delta difference between each increment might become large and negatively impact calculations. That would probably only be a concern with like procedural content generation. If you weren't renormalizing your coordinate system as the player's moving around, you may have seen games such as Minecraft. I've seen a few videos where someone will walk in one direction for hours and hours or even days, trying to find the end of Minecraft, and they start to see weird anomalies. And that is, I'm assuming, is related to the floats getting so big that the calculations are beginning to be impacted by the fact that with the large exponent, that you're no longer able to differentiate between tiny values, and so causing issues. So I would be concerned in those sorts of scenarios, but you could always like renormalize, reset the origin as you're moving. But yeah, really not anything to worry about in I guess reasonable circumstances in terms of this implementation. So this algorithm's got multiple steps. It's not especially complicated, but what we want to do is find the closest point on a line segment to a candidate point, so this or test point P. So we want to see how far our test point P is from our line segment. It's easier to define the problem if you're thinking in terms of an infinite line, because then it's we're just thinking about projection. So we can project. So in this case, we've got the two endpoints of our line segment, A, B, and then we've got P. So we want to project the vector AP onto AB. And so once we perform that projection, that's like we're dropping the point straight down. Like if you took your line segment and just made that your x-axis, and then rotated everything with it, like where P is relative, it would just be dropping P straight down onto the line. That's the effect of performing the projection. Now, if it's an infinite line, it could drop well beyond the endpoints of our line segment. So that wouldn't be the correct point to be measuring our distance from. So that's the next phase, is we want to see, well, if we did the projection and found the closest to the infinite line, is that point between the endpoints of our line segment? So if that's the case, then we would measure the distance from the projected point. We'll call that CP for closest point. So we'd just take we'll create the vector CP to P1, and then take the magnitude of that would be our length. But if our projection, that CP, ends up being on the outside of A or B, then we would pick either A or B. So if you're on the outside of B, you would pick B. And then if you're outside of A, you would pick A, because that is the closest point on the line segment to measure the distance from. So there's a lot of ways that we could set that up, but it'd be nice to have something that is efficient in terms of computation. And so I'm going to go through how to set up a reasonably efficient approach to this. So one thing that's always good in video games is to avoid square roots, or anytime you're computing something over and over, really, that tends to be a very expensive operation. So let's start off with working with like formal definition of projection. So here we've got a scenario where we've got vector B and vector A, and so we're performing a projection of A onto B. So that projected vector is going to be a scalar A1 times B normalized, so a unit vector form of B. So normalizing a vector just means dividing it by its magnitude. And so that scalar is that A1 scalar, not bold, but the I'll move my mouse over it. Hopefully, video encoding picks it up. So this scalar, which we see in the first equation, times the unit vector b, that is we can have in the angle form. So the magnitude of vector a times cosine of theta, where theta is the angle between vectors a and b, or more preferably for our case to use the dot product. So that would be vector a dot product with unit vector b. So that would be, if we expand how to calculate or substitute in for unit vector b, that would be vector a dot product with vector b over the magnitude of b. So if we take that and plug it into the first equation, the one on the top here, so we're going to plug this in. So recall that all of this that we got at the end is our scalar a1. So we plug that in for the scalar. So now we have the projected vector a with a little subscript 1 there, is equal to, in parentheses, vector a dot product vector b over magnitude of b, that's really the unit vector. And then that's times unit vector b, which we can substitute in there for how we get that as well, which is also vector b over magnitude of vector b. So we can simplify all of that, and then what you get is that projected vector a is equal to vector a dot vector b times vector b over the magnitude of b squared. Now this is nice because if you recall that the magnitude is the square root of sum of squares of the individual terms. So we're taking a square root and squaring it, so that cancels that out for us. And so that is getting rid of the square root, so that's a nice thing to have. The other thing we can do is that we can define a normalized scalar. So rather than using unit vector b to define where along the vector b we are, or in the direction of vector b, we can say that the projected vector a is equal to t, which is equal to all this stuff that we separated out from the equation on the left. So that's t times vector b. So we don't have the unit vector b. And what you're going to end up getting from that is that t value, it'll be 0 at the point, the beginning point of vector b. And if it's like 0.5, like 50%, it'll be halfway down the length. And if it's 1, it'd be at the very end of b. So that is nice to have, because when we actually calculate our projection to get that, if I go back slide to when we were talking about finding that closest point, that closest point is going to be defined by t. We're going to have this t in this nice form, and we can just check to see if t is greater than 1. And then we would, if it's greater than 1, we would know it's beyond b. And if it's less than 0, it would be behind a. And so in those cases, we know to just not use the distance from CP to P. We would instead use the distance from P to either A or B. So we just have some simple conditional logic that where we can look at T. So this is a nice little concise way of handling the calculation. We got rid of the square root, and then we've normalized our scalar to be in the context of the full length of B. So that makes implementation very easy. So there's only one other thing we got to watch out for, and that is if A and B, if those 2 points that define our line segment there, if they're the same point, because that would result in divide by 0 because we have this magnitude term here, and we don't want that divide by 0. So we need some conditional logic to test if A and B are the same. If they are the same, then we just have special case where the distance we return is going to be the distance from, you just pick A or B because they're the same, and just take the relative position vector between our test point and A or B, and then the magnitude of that, and that is our distance to the line, even though it's not really a line. But yeah, so that avoids the divided by 0. So this is a pretty straightforward implementation, but it has some nice little optimizations to it.